Hi everybody, I'm Greg Fishel. Welcome to bonus weather videos number 2 and 3 for this week. I am equating this video to 2 because we're going to cover some pretty complicated stuff in this particular video, and so I think it's actually probably the equivalent of 2, and so this will give me my quota for the week. So let's go on ahead and dive into this here, and what we're going to be doing is taking a look at a concept called vapor pressure, okay? And so what we're going to do here is start off with an empty container, and we're going to partially fill it with liquid water, okay? Now, to start off with, we're not going to have any evaporation at all. And so you've got water, and there are no water molecules above that surface of water, or that amount of liquid water, okay? However, we all know that evaporation occurs, and so as you increase the temperature of that water, more and more water molecules escape into the air above, and this is called evaporation. And these gaseous water molecules exert what is called vapor pressure, okay? So you have liquid water molecules, and then you also have gaseous water molecules, and those gaseous water molecules exert what is called vapor pressure, okay? Just like the air has pressure. Okay. So now we're going to talk about a little bit more about condensation and evaporation. Some of these gaseous water molecules then return to the water. In other words, they initially change from water to a gas, and then they go back from the gas to the water. And when that happens, we call it condensation, okay? Now, when the evaporation rate equals the condensation rate, we reach what is called the equilibrium vapor pressure, and the relative humidity is 100%. So there are as many molecules escaping the liquid state and going into the vapor state as there are ones going from the vapor state into the liquid state, okay? And when those two rates balance, then the relative humidity is 100% and the air is saturated. So vapor pressure depends on the number of water vapor molecules in the air and the condensation rates. And the more water vapor molecules there are, the greater the condensation rate is. The equilibrium vapor pressure depends on temperature and evaporation rates. So the warmer the air is, the more molecules that are going to escape from the water state into the vapor state. And so the temperature is affecting the evaporation rate, and the amount of moisture in the air is dictating the condensation rates, okay? You with me so far? Now, if we talk about relative humidity then is really the ratio of condensation rates to evaporation rates. When they're equal, the relative humidity is 100%. Now, we've talked about the dew point a lot over the years, and we've talked about how relative humidity really doesn't tell you how much water vapor is in the air. For instance, you can have the same relative humidity at a temperature of 30 as opposed to a temperature of 90, but there's 8 times as much water vapor in the air at 90 than there is at 30, okay? So the relative humidity only tells you what the humidity is or how much water vapor is in the air compared to the maximum amount possible at that temperature, okay? But it doesn't tell you anything about the absolute amount of water vapor in the air. So the dew point is determined by the vapor pressure, which is determined by the number of water molecules in the air. And so the more water vapor molecules there are, the higher the dew point is going to be. So by adding moisture to the air, you increase the vapor pressure, which increases the condensation rate, which then in turn increases the relative humidity, okay? And so if you think about it, let's say the temperature was 70 and the dew point was 10, okay? That would translate to a very low relative humidity. But if you increase the dew point from 10 to 30, that's going to double the amount of water vapor in the air, because about every 20-degree increase, it represents a doubling the amount of water vapor. So the relative humidity would go up, and then you increase the dew point to 50, and that doubles it again, and the relative humidity goes up. And then if you increase the dew point to 70, which is where the temperature is, then the relative humidity is 100%. Now, what about ice? Now, when ice molecules go straight to the vapor state, in other words, they don't melt, okay, in other words, you have solid ice, and if you go straight from there to vapor without going through that liquid state, we call that sublimation, okay? Sublimation requires more energy than evaporation, so the equilibrium vapor pressure with respect to ice is lower because sublimation rates are lower. It takes more work to do that, and so the rates are lower because it's harder to accomplish, okay? So if we put this in an equation form, the equation for relative humidity with respect to water would be the vapor pressure, which is dictated by the number of water vapor molecules, over the saturation vapor pressure with respect to water, which is determined by the temperature, okay? Now, the equation for relative humidity with respect to ice is this. The vapor pressure, again, the number of water vapor molecules, compared to the saturation vapor pressure with respect to ice. But we just said that the vapor pressure is the same in both of these equations, but the saturation vapor pressure is lower with respect to ice, then the relative humidity with respect to ice is going to be higher. If you have a fraction, you have a numerator and a denominator, and the denominator is smaller in the one equation than it is in the other, then that ratio with the denominator being smaller is going to be bigger, okay? And so the relative humidity is going to be higher with respect to ice than it is going to be with respect to the water. So the colder it gets, the bigger this temperature difference, or the bigger the difference is. In other words, at a temperature around 32, the difference between the dew point and the frost point is negligible, okay? But when you get colder and colder, that difference becomes pretty big. It can be several degrees. And so this is why precipitation growth, as you go up into the clouds and it gets colder and colder, is always going to be favored over ice particles as opposed to supercooled water droplets. And you can have water at temperatures well below freezing. We call it supercooled water, but the ice particles are always going to be favored for precipitation growth because of the fact that the frost point is going to be higher than the dew point, and so the humidity is going to be higher and it's going to be easier to achieve condensation. Okay, you've got less of a difference to make up between the frost point and the temperature and the dew point and the temperature. Okay. I hope that makes a little bit of sense. And one of these things about how when we talk about how water vapor or warm air can hold more water than cool air can, that's really not a scientifically accurate statement. It all really gets down to molecular motion, which is determined by temperature, how fast those molecules are moving, and that of course then determines what the evaporation rates are, and that determines relative humidity and everything else that we just talked about. So it really all gets down to the molecular level when it's all said and done. All right, folks, that is bonus weather video 2 and 3 for this week. Hope you have a great weekend and enjoy the warming trend, and we'll talk to you again on Monday. So y'all have a good one, folks. We'll talk to you soon. See you later.